Now students, we learn the second defect, that is Frankel defects. Frankel defects was discovered by Russian scientist Frankel in 1926. He observed in a crystal when an ion, it may be cation or anion, was displaced or missing from its normal lattice position or crystal points and occupies in a vacant interstitial site. It is voids between the lattice points, and due to this they create a vacancy and is termed as Frankel defect. Now students, we learn this picture. So what Frankel observed in a crystal, this is a picture of EGBr ionic crystal where silver and bromine ions occupied a lattice sites in a crystal lattice. But due to some condition, the silver atom, you see that, was displaced or missing from its normal lattice position or crystal points. So you have to see that the silver atom are missed from its normal position and occupies in the vacant interstitial site, that is voids in between the lattice points. So we have to see that. So cations, that is silver ion, migrate from crystal points to interstitial. Due to this, very interestingly, it create a vacancy due to this one atom, and this defect is called Frankel defect. Now very important, this defect observed in that ionic compound having low coordination number and the size of positive ions, that is cation, should be lower than negative ions. Cation must be fit into the interstitial site. Example, zinc sulfide, silver bromide, silver chloride, etc. So students, this defect observed in that ionic compounds where coordination number is low and the size of positive ions must be lower than negative ions. As you know, voids are very small in volume, therefore they must be fit into the voids. Now students, we have to calculate the number of Frankel defect formed per cm cube of the crystal is given by equation nf, small nf, is equal to under root capital N into n dash epsilon minus wf whole divided 2RT. So we learn what this term present in this equation, where nf is equal to number of Frankel defect formed per cm cube of the crystal. Capital N is equal to number of left vacant sites per cm cube of the crystal, and n dash is equal to number of alternative filled interstitial sites per cm cube of a crystal. So NF, calculate the number of Frankel defect, means missing of one ions, it may be cations or anions, and created vacancy, that is we have to calculate NF. How it is to calculate? So by the number of left vacant sites, that is capital N, formed per cm cube of the crystal, and N dash is to calculate the number of alternative field, the migration of ions from lattice point to interstitial site, that also important per cm cube of a crystal. W is energy required to form defects. It is Wf means the energy required to form Frankel defect. R is a gas constant, T is a temperature. And now very important students, due to these defects the density of crystal remains same. If you just understand the Frankel defect, the one ion, it may be cation or anion, is misplaced from its lattice points but is present in the interstitial site of a crystal lattice. So there is no any miss out, sorry, departed from the crystal lattice. Therefore, number of ions as it is present in the crystal, therefore the density of crystal remains same in Frankel defect. Now very important consequences of these defects are observed in a solid structure, that now we have to learn. Number 1, in both types of defects produces holes in the crystal. Heat and electric field moves by these holes when applied on a crystal ion. So very important consequence we have to learn in some time. Number 2 consequence, in Frankel defects similar charges come closer, therefore dielectric constants of the crystal increases. As cation in case of silver bromide, it goes to the interstitial site which is also near to the silver present in a lattice points, therefore positive are come close to each other, therefore dielectric constant of the crystal increases. Number 3 consequence, the presence of vacancies lower the density of the crystal. It also lowers lattice energy or stability of the crystal. As vacancy created in the crystal, absolutely density of the crystal also decreases. It observed as density decreases, the lattice energy or stability of crystal also get decreases. Now the first consequence we have to learn, student, this is a Frankel defect where silver ion is misplaced from its lattice point and present in interstitial sites. Now in this crystal lattice, when you apply the electric field, the electrons are occupied on these vacant sites and it moves from this. So in the next stage again silver ions are misplaced from its sites and occupy in voids, and the hole is created and electric field is passed from one end to another end in the crystal, and therefore that holes are created in the crystal are responsible for heat and electricity pass in a solid structure. Now students, we have to understand from the exam point of view the difference between the Schottky and Frankel defects. Schottky defects, Frankel defects. One by one we have to complete. In Schottky defects, in an ionic crystal, when cation and anion are completely missing from their lattice sites and create vacancies in a crystal lattice. What about the Frankel? In an ionic crystal, when ion, it may be cation or anion, is missing from its lattice position and occupies interstitial position between the lattice points. In this defect, Scotty defects, density of crystal decreases. In Frankel defects, density of crystal remains same. Now number 3 difference. In Scotty defects occurs in ionic crystal having high coordination number and the cations and anions have almost same size. 3 difference in Frankel defects. These defects occur in ionic crystal having low coordination number and cations is smaller in size than the anion. Last difference in Scotty defects, alkali halides like NaCl, KCl, etc. are the example of ionic crystal where this defect observed. And Frankel defects observed in silver halides, zinc sulfides are the example of ionic crystal having this effect. So you have to remember this difference between Scotty and Frankel defect. Now the conclusion part of this chapter. Student, summary of chapter. We have to start with the introduction part. Then we have to complete some important terms. Then we have to understand closest packing of rigid sphere such as in simple cubic, body centered cubic, face centered cubic. Then we have to come across efficiency of packing where we have to understand the atomic packing factor for SC simple cubic, body centered cubic, BCC and FCC face centered cubic. Then we have to perform numericals and the last part that we have to finish now, that is point defects. So I hope you have to understand this chapter and you have to revise and practice the numericals present in this chapter. Thank you.